Oh, hi. Didn't see you there. I was too busy playing this game on my iPhone. Just slide my finger up or down, left or right to direct my character. Such intuitive controls. But it got me thinking, how does the iPhone touchscreen work? Well, I'll tell you. It's called a capacitive touchscreen, and it works by virtue of a thin conductive layer that sits on top of the optical part of the screen. Now, an electric current is run through the conductive layer, and when you touch the screen, your finger as a conductor modifies the current. The iPhone has software to measure the modifications that take place, and it can determine the location of your finger based on these calculations. Now, the material they use for the conductive layer is called indium tin oxide. It's actually a semiconductor, and unlike other conductive and semiconductive materials, it's transparent at the optical spectrum. This means you can see through it. It's important that it's transparent because it has to sit on top of the optical part of the screen. Let's have a look at the structure of indium tin oxide to understand why it has these key properties of transparency and conductivity. Firstly, understand that indium tin oxide is a solid solution of indium oxide and tin oxide, typically 90% and 10% respectively in concentration. Indium oxide forms this structure, known as a cubic Abitbiite structure, and when doped with tin oxide, the indium 3+ atoms are replaced with tin. The tin forms covalent bonds with oxygen and results in tin oxide with +4 valency. This means that tin oxide is free to release these electrons into the conduction band, a gas of free, unbonded electrons present in conductive and semiconductive materials. The fact that these electrons are free to move throughout the substance gives indium tin oxide its conductivity. But, like we said before, the conductivity of indium tin oxide isn't particularly special. What is special is that where most conductive materials are opaque, indium tin oxide is transparent. Now, the mechanics behind this are quite complex, but put simply, in something of the same way as there are places where there is a high likelihood of finding an electron, the orbitals, and places where there is a very low likelihood of finding an electron, there are specific amounts of energy that a specific electron can and cannot have. Light and color is made up of elementary particles called photons, which each have their own specific amount of energy. Transparency of matter is determined by whether the photons that make up the visible spectrum have enough energy to excite the electrons of the matter in question into the next highest energy state. If the photons do not have enough energy, then the material will be transparent to that particular photon. What does that mean? As an example, let's take an imaginary bound electron and some imaginary photons with imaginary amount of energy. Our imaginary electron can only have 10 energy or 20 energy, nothing in between, so no 15 energy. Right now it has 10 energy. If a photon with 5 energy comes into contact with it, then they will not interact, as the electron cannot absorb the additional 5 energy. It needs at least 10 to move to the next energy level. The photon simply continues on its way and out the other side. If all the matter is composed of electrons that need to be at 10 or 20, then this photon will pass through everything, thus rendering the material transparent. On the other hand, if our photon had 10 energy, then the electron is able to absorb the energy of the photon and move up into the next energy band. The photon no longer exists and therefore doesn't come out the other side of the matter to be perceived as light. This is what happens in the case of indium tin oxide, as no photons in the visible spectrum have enough energy to excite any of the electrons into the next band. Now all this is well and good, but the reason transparent conductive materials are not common is that conductive materials have free electrons. This is how they conduct electricity. These free electrons are not bound to a nucleus and as such can have the same frequency as any photon. As to how indium tin oxide is both conductive and transparent, I can't shed any light. If anyone can tell me, I'd be very happy to know.